Welcome back to our course, Fundamentals of Operating Systems, based upon the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter B. Galvin. We just finished a lesson on process synchronization in which we identified a problem that exists when multiple processes interact with shared data or common data at the same time. In this lesson, we're going to follow up on that one and try to find some solution to that problem. So let's get started. Now what we're going to do is start considering process synchronization by discussing the critical section problem. Consider a system consisting of a number of processes as shown here. Each process from P0 to P whatever has a segment code called a critical section, in which the process may be accessing and updating data that is shared by at least one other process. A requirement of the system is that when one process is executing in its critical section, no other process can execute in its critical section. That is, no two processes are executing in their critical sections at the same time. The critical section problem is to design a protocol that the processes can use to synchronize their activity to cooperatively share data. Each process must request permission to enter its critical section. The section of code implementing this request is the entry section. If no other process is in its critical section, then this process may continue. The critical section may be followed by an exit section, and the remaining code is the remainder section. The general structure of a typical process is shown here. The entry section and exit sections are enclosed in boxes to highlight the importance of those segments of code. A solution to the critical section problem must satisfy three requirements shown here. While I may be criticized for reading something that you can read yourself, I think these requirements are important enough to justify it, so here we go. First requirement is mutual exclusion. If a process is executing in its critical section, then no other process can be executing in their critical sections. Another requirement is progress. If no process is executing in its critical section and some processes wish to execute in their critical sections, then only those processes that are not executing in their remainder sections can participate in deciding which will enter its critical section next, and this selection cannot be postponed indefinitely. Thirdly, bounded waiting. There exists a limit on the number of times that other processes can enter their critical sections after a process has made a request to enter its critical section and before that request is granted. We assume that each process is executing at some speed, but we don't know the relative speed of each of the processes. At a given point in time, many kernel code processes may be active in the operating system. As a result, the code implementing an operating system, that is the kernel code, is subject to several possible race conditions. Consider as an example a kernel data structure that maintains a list of all open files in the system. Since the list must be modified when a new file is opened or closed, if two processes were to open files simultaneously, the separate updates to this list could result in a race condition. Other kernel data structures that are prone to possible race conditions include structures for maintaining memory allocation, for maintaining process lists, or for interrupt handling. It is up to the kernel developers to ensure that the operating system is free of such race conditions. The critical section problem could be solved simply in a single core environment if we could prevent the interrupts from occurring while a shared value is being modified. In this way, we could be sure that the current sequence of instructions would be allowed to execute in order without preemption. No other instructions would be run, so no unexpected modifications could be made to the shared variable. Unfortunately, this solution is not as feasible in a multiprocessor environment. Disabling interrupts on a multiprocessor can be time-consuming since the message is passed to all processors. This message passing delays entry into each critical section and the system efficiency goes down. Two general approaches are used to handle critical sections in operating systems: preemptive kernels and non-preemptive kernels. As we've already learned, a preemptive kernel allows a process to be preempted while it is running in kernel mode. A non-preemptive kernel does not allow a process running in kernel mode to be preempted. So in this case, a kernel mode process will run till it exits kernel mode, blocks, or voluntarily yields control to the CPU. Obviously, a non-preemptive kernel is essentially free from race conditions on kernel data structures since only one process is active in the kernel at a time. We can't say the same about preemptive kernels. So they must be carefully designed to ensure that shared kernel data are free from race conditions. Preemptive kernels are especially difficult to design for symmetric multiprocessing architectures, since in these environments it is possible for two kernel mode processes to run simultaneously on different CPU cores. Why, then, would anyone favor a preemptive kernel over a non-preemptive kernel? For one thing, a preemptive kernel may be more responsive since there is less risk that a kernel mode process will run for a long time before relinquishing the processor to waiting processes. Furthermore, a preemptive kernel is more suitable for real-time programming as it will allow a real-time process to preempt a process currently running in the kernel. Okay, we've been introduced now to the critical section problem of process synchronization. Let's take a break right here, go over your notes, review what we've just talked about, and when we come back we will start looking at some approaches to dealing with this, starting with one called the test and set. So when you're ready, come on back and we'll continue.